Hi folks, welcome to the video on NetworkX package, and this package is specifically used for drawing networks, and networks are basically specified by nodes and edges, and nodes can be many things. Like for instance, in a friendship network, a node will be person and the edges will be uh, relationships. Like in Facebook it will be the friendship, in Twitter it will be perhaps it will be directed edges, will be following, whether you follow somebody and they follow you back. Okay, so once we have this, we can calculate certain measures of network connectivity and network influencers. Okay, some of examples of this is in NetworkX examples.zip. I'm going to go over those examples with you. Now right there, if you go to online website, our class website, you'll see that they are available there, and there are a bunch of examples in here. Okay, and there is also I posted, not related to this package, but there I also posted a bunch of other problems that we're going to touch upon. One of them is the Facebook, and there are a bunch of other examples for Seaborn graphics library. Okay, so let's get to it then. Now, a network, as we said, consists of nodes and edges, and like for instance, it could be individuals, and then nodes could be relationships, as I said earlier. So some networks could be symmetric, and could be others will be asymmetric, and sometimes it will be uniform or weighted networks. So the relationship could be weighted by the strength of the relationship, and the direction could be also another concern that we need to have. Okay, like for instance, Twitter is not symmetric versus Facebook is a symmetric network. Now the network can be evaluated by its connectivity. Now each node in a network will have a degree. Degree is basically a number of connections a node has. Now, of course, there could be in degree and out degree if the network is not symmetric. In a symmetric network, degree is degree, it doesn't matter, right? But in a asymmetric network, there could be in degree, meaning how many people follow you, and out degree is how many people you follow, okay? And then one of the coefficients is, one of the measures of network connectivity is something called clustering coefficient. It's basically nodes that share connection in a social network usually are in a cluster, and we basically measure this clustering level using clustering coefficient, and basically we define what is called a local clustering coefficient, which is basically the fraction of pairs of the node's friends that are connected with each other. Okay, so I have friends, and how many of those friends are also connected with each other? How clustered are we in terms of our relationship? And distance is basically a measure of distance between two nodes. How far, how many hops you have to take before you can reach to the other end of the relationship. Okay, so it's basically the path between two nodes. And finally, the eccentricity is that a node, which basically is the largest distance between a node and all other nodes. Okay, and how eccentric a node is given its relationship between within the network. Okay, let's put it that way. Networks also have measures in terms of their influencers. Like one of the measures of this is degree centrality. So it means the people who are in the center of a network, they connect a lot of people. Okay, so it's basically this is a measure of number of connections a specific node has, and then important nodes necessarily have a lot of connections. And Google's algorithm is also based on this, right? So based on this centrality of degree. Okay, how many nodes point to you, and how many nodes you point out. Okay, there's also something called eigenvector centrality. So it's not only that how connected you are, but how connected you are to other people who are also important. So Google's PageRank considers this as well. So it means how many people that are important themselves are pointing to your web page. Okay, so that shows you how influential your page is. So the Google's original idea, page rank idea, actually is based on this. Okay, based on eigenvector centrality. Not only how connected you are, but how connected the people who are connected to you are. Okay, so you can think of it in that way. And the final measure of network influences is called betweenness centrality. It's basically if you have, let's say, two groups, okay, and there is usually this, there's a path that connects these two groups, okay, and how often a person is on that path it's basically, it's betweenness centrality, okay. So that means you take the shortest path between two nodes, and then you remove the nodes that have basically they are central, and you measure the length. If the length changes drastically, then this basically node is very central. So it's between many nodes, and it actually changes the shortest path. So if the node changes a lot of shortest paths, then that node is in between. So of course there are formulas for each of these, but I'm not going to go on to the formulas, but we're going to talk about basically the NetworkX package, which can actually allow us to create a network, and based on these measures, and then perhaps given the network also calculate these measures for us. Okay. So the package is NetworkX, and so let me get my Wing going. So I'm going to actually do this with Wing. All right. I'm going to start with an example, plot football. Now, this example has basically data for American football, college football, for year 2000. Okay, so basically here is the description. You can read that, but it basically tries to see if Python 3 is available. If so, it uses that. If not, it basically uses Python 2, and then imports IO, and it imports different files based on whether it's 3 or 2. That's why it has these try except block. And then it imports IO, it imports zip file. So IO is for input output, right, and reading through a stream, and zip file is basically downloading files. Okay, and then typically you have your pyplot and matplotlib pyplot, and then we have NetworkX. Okay, and then here is the link URL. This URL is basically where the data is. It's in a zip file. That's why we have to have this zip file imported. So what we do is we open a connection using a socket, right? Open a connection to this URL, and then we read whatever that URL gives us and put it into a variable called S. Once we have that variable, we then use our zip file package to open that package and then go ahead and read files inside. So there are two files in that zip file. One is txt, football txt, another one is football.gml. The first one is the info file, the second one is the data for the network. Okay. Now, and then we basically throw away the bogus first line. We do that, basically take the GML and split it by \n, so each row, and then we take the top row and throw it away. How do we throw it away? We basically use our slicing. So we slice, instead of starting from 0, we say start from 1 and get everything else. So that means remove the first element in that list. Since we create the split function, remember, it creates a list, and we basically throw the first element of the list and rename our list. Then we basically use our library, an X library, which is basically NetworkX, and then parse this GML. So once we parse the GML data, and we have basically G, which is the graph. So we define this to be a graph, and the package NetworkX actually allows us to, based on this GML value, we can actually go ahead and create a network. Now the network actually shows which team played which team. So let me go ahead and run this. So this is what it looks like. So here is the network of American football teams. So each team, I don't see the names yet, but I'm going to put the names shortly. So these are all teams that played each other. This is not a geographical network, it's just a network based on their playing each other. All right. So let me close this. All right. Okay. All right. So you notice now it prints at the top. It prints the information. So let me get rid of this. Don't need that space. So here talks about, for year 2000, here are the games and here are the conferences, and each conference you basically have these teams, and this is basically for each team how many games they played. All right, and then you go through this, and then you, based on these and the games between the them, and you basically go ahead and create a network. So the network itself, so here the degrees are printed, so it's basically the degree of each node, right? The nodes are basically teams. Then we basically go ahead and draw this. There is a draw method in network package, which basically takes any graph which has basically nodes and edges, and takes that and prints it. You notice now the options for this specific function are given right here. So basically the options are a dictionary. So the dictionary has, each key is the option itself, the value, option itself, value, and then we basically put this inside using this double asterisk. Remember this? We basically put these as keyword parameters, and then we unpack these and send them. So instead of doing this right here, so we are doing this one by one. So I'm going to go ahead and add one more option. That option will be, as far as I remember, it was with labels. Right? So it says whether the labels are printed or not. By default, it's false. I'm going to turn it into true. Okay. So now, right. Right. So here is one more option. I'm going to go ahead and print. Now, what it will do is, it will go ahead and put the labels. Okay. Let me make this a bit larger so you can see what we're doing. So here are the teams and their names. We can actually see Florida somewhere here. Where is Florida? Right here at the bottom, Florida. Right, so it played Tennessee, Georgia, Kentucky, Vanderbilt, South Carolina, Mississippi State. So those are the teams that we played, and we played also Western Michigan as the opening game. I think that year we also played Miami of Ohio, it looks like. Okay, I was a student at UF at that time, actually. Interestingly, I very well remember the Tennessee game. That was a backbreaking game, to be honest with you. All right, so this is a network. So as simple as this, you notice we basically draw these, use the network package. All we need to do is just give it nodes, and it can actually turn it into a graph. By default, NetworkX package has all kinds of graphs as well. There are default graphs that we can actually go pick up and draw. So either we have our own graph or we pick one from the library and draw it. So let me show you one from the library. The one from the library, well, Karate Club is from the library too, but let me get with a small one. I'm going to start with Simple Pad. Okay, let's look at Simple Pad. Right, this is the simplest as possible. So we, import two packages, and then we basically say, okay, here is a path graph. This is the simplest graph, and then I have 8 nodes in this. So if I print this, you see that there will be 8 nodes, and they will be all connected to one another. Okay, it's a simple path. I can change the size clearly. Let me make it. See what happens. All right. So you notice now it's randomly going through a single path. All right. So you can actually do 10. Right. So you can actually, this creates a simple path for you. Right. That's all. It randomly places them on the screen. Places the first one randomly and then goes from there. Okay. Same distance, equidistance, but the angle changes. All right. Next is, I want to save this. I'm going to show you Karate Club. Again, this is a library which is built in. All I'm doing is actually getting the Karate Club graph. Okay, So this basically looks something like this, a circular graph. So this is how I'm drawing it. These are the connections, okay? So these are the club and its members and how they are connected to each other. I think through games, as far as I remember, okay? It's a very common graph. So you can actually use this circular graph library and give it nodes and edges. That's all. This is just, G is just nodes and edges, okay? You can actually go ahead and print. See, you can print each node and look at their degrees. You can here see the degree. Node 2 has a high degree, node 0 has the highest degree. I think 16, that's the highest, okay? And there's 17 even, 33, so let's look at that. So the nodes with high degree are on to the right. So 0, 33, 32, these are high degree nodes, and the ones that are low degree are to the left. All right, so that is there, built in. Okay. What else? So we can also create, given the plot, we can create what we call a degree histogram. So let me run this. You'll see actually what it will do is it will create a given network. It will create the network, and also it will have the nodes and how many nodes have what degree. Okay, so here 10 nodes have 0 degree. About 20 nodes has degree 1, and then 30 nodes have degree 2. So if you notice, these 10 nodes are the nodes right here. So they're not connected to anyone. So that means their degree is 0. And then you have nodes, these are 1, all 1, right? So this is 1, this is 2, right? This is 1. So anything that's on the corner is degree is 1. Okay, so on. Okay. So how do we get these graphs? So the graphs are actually, we get by, so at the top. Okay, here we go. So we basically get it through a random graph. So what we do is we take 8 nodes, 10 nodes, 100 nodes, and this is the density of this graph, how connected the graph is. So if we make it 1, okay, so this will be very heavy. Right, so that means it's very dense. So that means every node is connected to every other node. So you'll see now it will be all degree. So everybody has a degree of 100. All nodes are connected. You see that all lines are, it's all black. So it's too much. So let's make it 0.5. That means everybody is connected to half the network. Okay, this is something like this. So you will have some distribution and still a very dense network nonetheless. Okay, so by changing this to two values, density of the network, and you can actually, and the number of nodes you have, you can actually create a random graph. So based on this random graph, we then go ahead and create the graph. We basically look at the degree histogram. So this is the port that creates the histogram itself. So once we have the axis, and then let me see, this is where we draw. Okay, so we draw the network. This portion draws the network on the screen, and pie plot here, this draws right here, starting from here, it draws the histogram itself. This part draws the histogram and then modifies it, sets the ticks and all that. So this is very similar to what we did in our previous class. Okay, so I don't want to go into every single detail, but this is how it works. Okay, so one last thing I have to do here is, I have two things actually, but let me do this, read and write. So this basically creates a graph, grid graph, y.5, and then goes and reads that. So let's look at that graph. So here's the graph. So this is what the graph is. Ooh, interesting graph. So every time I play with this, run this, you see that it will be a different graph. Okay, so let me run it one more time. It will be a totally different graph. Okay, in terms of how it's situated on the screen. Right. So then this is how the nodes are connected to each other. Okay, and this edge list is also split out, so it's actually written right here. So let's see, write edge list. Okay, so we are writing edge list and right here, so it's written as a file. You can take a look at it. So here is the edge list. So this is called an adjacency edge list. So this is how a representation of a network. Okay. All right, let's close both of these. Yeah. I don't want to save any of that. The final thing I'm going to show you here is the plot by words. So this is basically an example created by a famous computer scientist, Donald Knuth, and he was a professor at Stanford University. And this example, basically we are getting this file called right here, words underscore that underscore txt gz, and we are using a specific import. This is a gzip, so basically a zip utility. It allows you to unzip a zip file. So this is a zip file and zip through a gzip. So I'm going to unzip that. So here I'm going to take the data and unzip it. So right here, so I'm going to open the file called this file and read only. And once I open this, I basically create a set words and go read by read, one by one, and adds word to this, add each word to this set, right? So they're not repeated, so they're added one at a time. So this function basically creates the word graph, and then main actually tries to find the shortest path. Okay, so it finds the shortest path between two words. So the connection between a word means if one letter is different between two words, they are connected. So what we're going to do is we're going to actually look at the word list, and using that word list, see if chaos can be connected to order, nodes can be connected to graph, and pound can be, by changing one letter at a time, can be connected to marks. Okay, so it's going to find the shortest path if there is any. If not, it's going to print, if there is, it's going to print the shortest path. So, and if not, it's going to say none. So it basically finds the shortest path using a function by, on this graph, the graph is the one that is given by the words that are in the in the file itself. So finally, the function that creates the graph from the words is the function right here. So words graph. So it's basically right here. It creates the words graph. Okay, right here. So basically, we generate a graph. So we send this, and the generate the graph is right here. So this is the that calls that function, and this generates the graph. Okay, take the words, right, and then you go ahead and take the distance, and you go find how the distances can be calculated. Okay, so I don't want to get into the detail of this, but this is basically the graph is created right here. Okay, so it finds the edges one at a time. So when we run this, you'll notice that it will show you how you can reach from chaos to order. So you can reach it in this shortest path, right? Chaos to coos, shoes, shows, shoot, shred, side, sided, edit, and added, and adder, and order. Okay, order and order, and then it finds the shortest path between nodes and graph, and then finally says there is no shortest path between pound and marks. Okay, that's none. Right, so that uses. So the file itself, this zip file, if you actually double click on this, you'll see that there is a text file underneath this, and this is what that text file looks like. Okay, so here's that big text file where all the words are. Okay, right, all the 5-letter words. Right, all the way down. Right. All right. So the overall, if you want to look at the NetworkX library, so it has a nice site. In the site, you notice the draw function has a bunch of attributes: the node size, the edge list, node list. You can change all that, alpha, transparency, the colors, the widths, labels. You can add labels, font size. You can change all that using these options. So when we draw them, you notice we didn't have much options. So for instance, in this example, this one, read write, see that we had no options when we draw. We can actually have options too. We can actually say node size, we can change it to, let's say, make it 20. Let's see what happens. Okay. See now, it'll be smaller nodes, right? So by default, it's, I don't know what it is, but let's make it 100. So it could be 100 perhaps, right? So default is somewhere close to 100. So that you can change all those options. Go to this website network, you can search online, and you can see all kinds of things that you can do. There are all kinds of graphs as well. So default graphs, you can actually go look at what library graphs are available. We have seen circular, we have seen path graphs, there are others as well. All right, so this wraps up the NetworkX. The next thing I want to show you briefly is these plot examples. And let me close this, and let me close this file as well. I'm going to open some of these. Right, so let me open Facebook. The Facebook is actually is based on a network of Facebook users at Stanford University. So it's in this file. So right here, Facebook combined. So it's a zip file. So we open that zip file, and here is the text file. We read that text file, and then based on that text file, we create a network. And then I'm going to calculate the network first. It takes quite a while. Okay. So let me do that. So it's going to run. I don't know if it will finish, but it should look something like this. I think I have. This is what it will look like. Once it's finished, it's going to look like this. Okay. So this is a network of relationships at Stanford Universities, and then it shows you all the connections on that network. So this is running. So you see, it finds the number of nodes. There are 4,000 people, and then there are 88,000 edges, and average degree is 43. So that means on average, a person is connected to 43 other people. Now, I want to show you a few things here. One is, forget about the network creation. So here are the colors. You see, we create node color and node size. We randomize this. So the node color is changed by the degree. So we calculate the degree of each node, so each vertex, and change the color. And then we calculate the betweenness centrality, okay, right here, betweenness centrality. And then we choose that for each node, we use those values to make the size of the node different. Okay, so the node that's bigger means it's connecting everybody, so it's in the middle of people, and then the nodes that are smaller are not connecting anyone. Okay, so that's what it means. They don't have high betweenness centrality. Okay, all right, this is still running. So let's go back to this. So here are the nodes. These big nodes are connecting a lot of people, so they're connecting. So this one, you notice this is connecting. It's not connected to a lot of people, so it doesn't have a very high degree, but it is at a central location. So if you take this out, this node, then this huge portion and this huge portion will be disconnected. You notice now there'll be no connections left. So that's because of that, this has a very high betweenness centrality. This node here as well. You notice there is this chunk, this remote chunk, okay, and this actually connects the network to the rest. Okay, same right in the middle, and there are a few others right here. So you see that each cluster has one node, right, connecting it to the other, so that node has the highest betweenness centrality. All right, so that's this. This is still running. It takes quite a while. I mean, this is a lot of nodes and a lot of connections. It will come up. It will print something like this, but it will take a while. Anything else? So while it's running, so let me look at other. Hopefully it will continue to run. So I'm going to look at a few other plot examples. So one is called Anscombe quartet. This actually plots the Anscombe quartet, and you notice actually, if you open this up, you'll notice that actually there is a default data set which is Anscombe. So you can actually go ahead and download. So what you're doing is Seaborn library has these default data sets that you can use. One of them is Anscombe. There is other one. So the other one here, this one is, let me see, right here. This box plot example, it uses tips dataset. Tips dataset is actually a restaurant dataset. So you basically have restaurant attendance and people, coming to the restaurant, and then how much they tip. It's very nice dataset. I think this is not gonna finish in time, so I'm gonna go run some of these. Okay, so but anyways, if once you run this, you have to get a graph just like the one I showed you. Oh, here it is. Before I could finish, here is the graph. It's a bit different than what we have, but nonetheless, it is some network graph. So their same graph is organized differently. That's all. Right. So let's close that. So let's look at the tip. So what it will do is it will give me a group. So let me do one more. So let me do a while this. I think this is the tip data set as well. So this is used the, let me see. Yeah, it basically shows me a violin plots. Okay, it's not this. I think this is the good. So let me just run this. Okay. So here is a group box plot. So here basically you have group of, for Thursday attendees, you have smokers and non-smokers. Smokers and non-smokers, how much they tip. Okay, so here, the box plot for smokers, box plot for non-smokers. Okay, all right. So this, you see that Sunday smokers they tip more, but Friday and Thursday smokers actually they don't tip more than their non-smoker counterparts. Interesting. So Saturday, Sunday, actually people who are smoking, they're most likely they're drinking. That's why they tip more. They're merrier in that sense. Okay. All right. So that data set is internally available. So that means you can go ahead and load and play with it. Okay. There is one more plot. This is also very nice, very simple. But let's look at what this does. So we take the tips database again. We create this joint plot. I've shown you this before. Right, and then there is this line fit. There are what do you call the reference? The word just bands. They are called reference bands. Okay, so you get these reference bands, and then these are the points. So this is the total bill and how much the person tipped. So here's a distribution of the bills, right? Somewhere around like $15 on average. Okay, and then the tips are around $2. And then some people tip more and some people tip, not less. They don't tip so little. So this is the tip database. Beautiful. All right, anything else? This one. So this is now the facet graph that we have seen before. So this basically, remember, this is the facet grid. Now, it's basically what this does is uses the time and then creates you the histogram for each time block. So this is what it looks like, right? Right, so it basically shows you lunch and dinner and sex, meaning male and female, and how much they tip. All right, you notice what's happening here? Dinner, definitely people tip more. Okay, so the bill is more, clearly, it's higher, but they tip more. And of course, then more people have dinner than lunch. On top of it, you notice males actually are on the tip side. So let's look at the tip. This is the total bill. There's no tips here. This is just total bill. You see that males spend more, it looks like. Well, kind of, not much. But there are more male pairs than female pairs, at least that you can see. All right, very nice data sets. I wanted to share this. These are all available. The data sets are available. I'm not loading anything, you notice. I'm using only the default database that are available in Seaborn, so that you can actually use these and play around with these functions and learn how they respond. Okay, especially how I change these options. Okay. All right, this is all. I'm gonna stop here, and hopefully I'll see you later. Bye bye.